If I don't like the rating value on my given capacitor, I can change it. I can take capacitors and connect them in a network in either what we call a series arrangement or a parallel arrangement in order to change the values. So this is a 14,000 microfarad capacitor, which I think you would agree would be the same thing as a 14 millifarad capacitor. If I wanted 28 millifarads, I could take two of these and connect them in parallel. If I connect two of these 14 millifarad capacitors together in series, then it'll actually go down to 7 millifarads. So connecting two together will produce half the amount of capacitance. But the benefit in that series case will be, instead of having a 40 volt limit before I make the insulator stop insulating and start conducting, in other words, before I break my capacitor, by putting them in series, I would double the maximum voltage limit. I would change it from a 40 volt maximum limit to 80 volts. Yeah. Let me show you what I mean by series and parallel connections. If I want to put these three capacitors together in series, then I'll take, I'll start with just one red wire and connect it to the positive terminal here. And I'll take one black wire and connect it to the negative terminal here. Now I guess from here I shouldn't use either black or red wires, because I'm going to connect one from the negative terminal of this one to the positive terminal of this one. So maybe in that case I'll use a yellow wire, right? And then I'll use another yellow wire to connect the negative of this one to the positive of this one. So there's really only one pathway. I think of it like a maze, and you've got to get from the start to the finish. Well, okay, go through this wire, go through this capacitor, go through this wire. There's just one straight line path. If we stretch this out, we can see it that way. And so how would I diagram that? Here, hopefully you can see on this. If I take one red wire out of this one's positive terminal. Now let me do it on this diagram here. One red wire out of this positive terminal, one black wire out of this negative terminal, and then I connect this one's positive to this one's negative, this one's positive to this one's negative. There we have it. One single line as represented by this schematic diagram, okay? There's the positive, there's the negative. So what about parallel? Well, parallel, I might do something like this. I'll still take one red wire out of this positive, one black wire out of this negative, but then I'll connect all the negatives together, and I'll connect all the positives together, and now they're connected in parallel. There's not just one pathway, right? So it would look like this. We'll say those are all the negatives. Here are all my positives, and I connect the positives together. I connect the negatives together. And then I can come out of any one of these. I could take one red wire off of this one. I could take one black wire off of this one or this one. It doesn't matter which one. Basically, the electric potential is low at all these points. In other words, this is all at the same low electric potential. This point, 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 these are all high potential. And so the potential difference, high to low across this capacitor, is the same potential difference high to low across. All three of these capacitors have the same what? The same difference in electric potential, or in other words, they all have the same voltage. Now in this series case, they don't necessarily all have the same voltage. Now if these are identical value capacitors, then they would have the same voltage as each other, but there's no guarantee these are the same value capacitance as one another. So let's say I had connected this maybe overall to a 12 volt battery, like a car battery. It could be possible that the first capacitor has 7 volts from its low potential side to its high potential side, from its negative to its positive. And then if I measure the potential difference, not from point A to B, but from point B to C, well, that could possibly be 3 volts of potential difference. And then if I compare the relatively lower potential at C to the highest potential of all at point D, right, closest to the positive terminal of my 12-volt battery, then that would have to be 2 volts. So if I add it all up, 7 plus 3 plus 2, it gives me the total voltage. So we might refer to a series connection as a voltage divider, right? So is there any quantity that's the same for all of these, even if they're different values of capacitance? Yeah. Because this one metal plate is the only one that has a direct connection to the negative terminal of the battery, that's the one on which electrons accumulate. Now, where did those electrons come from? They came off of this very bottom plate that's connected to the positive terminal of the battery. And so those electrons got carried through the circuit and then through the battery and here, and by conduction, we've conducted electrons off of this bottom positive plate and onto this top negative plate. Then charge by induction takes place. This plate has no direct contact to the battery. After all, the material between these plates is dielectric or insulating, but because of charge by induction, it gets a positive charge that mirrors or matches the negative charge on this plate. And likewise, this plate becomes negative, this one becomes positive, this one becomes negative, and so the charge really on any capacitor is how much? 0. Capacitors don't store charge, they store energy. They store positive charge on their positive plate and negative charge on their negative plate, but in total, each capacitor has 0 charge. And in fact, the whole network in total has 0 charge. But the charge on any one of them, Q number 1, Q number 2, and Q number 3 are all the same. So capacitors connected in parallel, by definition, always have the same voltage as one another. Whereas capacitors connected in series, by definition, all have the same charge as one another.